All right, line P1, we're in learning test 6. We're going to take a look at transformer connections and applications. So we've looked at the basic ideas of transformers, the way that we can stick a voltage on one side, we change that electrical energy into magnetic energy, and then we pass it over to another side. And the side that we come in on, we call that the primary. The side that we go out on, we call that the secondary. We can use those transformers to either step up or we can use them to step down. But all of the transformers that we looked at before were what we would refer to as a single coil design. In other words, there's one winding that is going to be my high voltage, one winding that is going to go and be my low voltage. This one here could be the high voltage, this one here could be the low voltage, if I was doing a step down application or whatever it was. But we only really had one option to go and use them at. I could only use this if I had the proper high voltage value of voltage and the proper low voltage value of voltage. What we more commonly have is we have what's called multi-coil transformers. And a multi-coil transformer is going to be a transformer that's going to look like this and have multiple coils that we can go and choose to either series or parallel together in order to go and achieve different operational values of voltage. They give you right underneath the figure 1, they talk about what the ratings of this transformer that we're going to take a look at are. And the ratings for this transformer are going to go and be 100 kVA. Let's stop right there before we take a look at the voltages. What have we talked about with kVA? Well, in the last learning task, we talked about that if I have got a transformer that has got a split winding, each of my two halves is going to be good for half of that kVA. So if I wanted to, I could just kind of draw a dotted line down the center over here and say this half over here is going to be good for 50 kVA, and this half over here is going to be good for 50 kVA. In other words, this winding is going to be good for 50 kVA, and this winding, its matched pair, is going to be good for 50 kVA as well. Anytime that we have a transformer, and where it's multi-coil, it will always have to be an even half. If I did not have an even half, I would have an unequal number of turns. And if I had an unequal number of turns on the primary over there, then I would run into problems where I'm going to have unequal values of voltage. And I couldn't actually go and use this thing in the same way for series and parallel. So that's our kVA part. The next part that they talk about is going to be the voltage part. And so what they give us is they give us some slash ratings and then a hyphen. So before we even write out what it is, we need to identify what our slash ratings themselves actually are. If I've got a number that is x, slash x, and then a hyphen, and then another x slash x, what I'm going to be seeing is this hyphen over here stands as my break line for high side to low side that we are going to go and have. The slash rating talks about the same winding. This winding could be this or this. The slash is sometimes used inside of certain types of coding, and it's an or type of statement that we have over here. So it could be 2400 or 4800. If I take a look at what this is rated for, they tell me that this transformer is 100 kVA, 2400 slash 4800. So because there's slash, that means they're on the same sign. Dash 120 slash 240. So this is now going to go and tell me that I've got a high voltage side that could be connected for either one of these. I've got a low voltage side that could be connected for either one of these. I don't know if you remember from the last learning task, but we talked about the second number is going to be the series connection, right? So the second is the series, the second is the series when we're looking at this, when we're looking at them in proper layout. Now here's where we could have some issues. Not every transformer is going to be laid out properly inside of all, problems and books, etc. There is what is called standard notation. And the standard notation identifies for me a couple of things. This over here is done properly in standard notation. Standard notation tells me that this is a single phase transformer. And I know that because it goes with the low, then the high in the slash rating. If I have a 120, 240, I know that whatever that piece of equipment is, it's designed for single phase. If I have got something that is 208 slash 120, we haven't covered 208 value volts is three phase, we'll cover that next year. But if it's 208 slash 120 where it goes high-low, then it's going to go and be a three-phase type of connection. So the fact that the second one is going to be your series connection, or that the larger one here is our series connection, only works when it's written in the proper notation, which is going to be going from low to high. Low, high, low, high. Just like that over there. Okay? Anytime that you see that, the high and then the low, it's usually indicative. If it was written, intentionally, it's going to be indicative of a three-phase type of system. It's widely misused, though, both of these ones. People just kind of throw numbers out there, and they're like 120, 240, or 240, 120, etc. Inside of the book, though, we are going to try to stick to, proper notation. All right, so going back to this one over here, if I've got 2400, 4800, the smaller one, whatever my smaller value is going to be is always going to be what my individual coils themselves are going to be rated. So if I go to my high side, and it's identified with my H's here, that's why we know it's the high side. Not because it's on the top. We can have the low side on the top. Depends if we're doing step up or step down. But I know that it's the high side because of the H's, so it's 2400. The smaller value of voltage for each individual coil. Same with this one over here is good for 2400. These low sides over here, each of the individual coils are going to be good for smaller value of voltage, 120. 20 and 120 that we are going to have on that one. Perfect. If I wanted to, at this point, I could separate my transformer along this line. You can't physically separate the transformer, but you could look at this side and you could take a look at it and you could say, well, if, and we're just going to go and pull this one side out to the side over here. Actually, we'll just do that. If that side of the transformer over here is good for 50 kVA, and it's got a high primary of 2400 and a low secondary of 120, what is my individual currents going to be rated for each of these sides? We'll cover all of this stuff later on, but right now, while we're dealing with this multi-coil, we should start with this right now. Well, we can go and take 50,000, that's 50 kVA. That's 500,000 there. 50 kVA, and we can just divide it by our value of voltage. So we'll divide it by 2400. When we do that, take 50,000 divided by 2400, I'll find out that this winding, this line itself, is going to be good for 20.8 amps. At the maximum, right? Doesn't mean it's necessarily going to have 20.8 amps. It's going to depend on what's connected to the secondary side for a load, but it could go all the way up to 20.8 and still be inside of its rated maximum. This one over here is going to be 120. Is it the same 50 kVA that side? Absolutely. So I can go and figure out what the current rating is of this section by taking 50,000 divided by $1.20. When we do that, we're going to come out to 416 amps. Once again, these are going to be absolute maximums, 416.7 amperes that we could go and have. Okay. That would mean that this side over here has got the same sort of capabilities. In other words, this winding could also put through 20.8 amps. And that this winding over here could also go and put through 416.7 amps. So we've taken all of our nameplate data, 100 kVA, 2400, 4800, 12240, and we've established just a bunch of different values. I'm going to suggest that until you get good with your transformers, that you do the same thing. It's just easier for you to, before you make your connections and start to sort stuff out, just keep that transformer disconnected and make these, calculations, figure out what each half is good for, figure out the maximum current that can go through each half, through each winding, and then after that, we'll worry about doing our connections onto a line. Okay, let's start with connecting this thing into a high voltage bus. We're going to use this thing initially as a step-down transformer. It is more common for you to be using step-down transformers than to be using step-up transformers. We're going to have a lot of installations where we're coming in at a higher value of voltage. 600, 347 is pretty common in the industrial and even in light commercial type of applications. But you're going to also want to have some 122, 240 inside of there so that you can go and run office equipment, computers and some lights and things like that. So we're very commonly going to go in from the high voltage, step it down to the low voltage. We'll start with that, doing a high down to a low type of connection. They give us two options, and the options that we could connect this to are basically going to be the two ratings that it was. Remember how this thing was rated at being 2400/4800. Those are my only two options that I can go and connect to. So let's take a look at connecting to a 4800 bus and a 2400 bus over here. If I want to go and connect them to a 2400 volt bus. We're going to start with a 2400, by the way. That would mean that each of my individual windings would have to go and be placed across from line to line. What they're doing inside of here is they're making what we refer to as a parallel connection. If I take a look at this winding here, I see H1 connects through all the way to H2. And H2 ties onto that line, jumps up to H4 over there. It's one way of drawing it. The other way that they could have drawn it, which is just as correct, would have been to take this line up like that. If you do that, still ultimately the same connection, because we're still going across from my line 1 over to my line 2. They just drew it over there and they shared that line going back out on the transformer. Erase that one there and put it back to the way it was. So I've got this one that has a full 2400 volts over top of it. I'm also going to go and have the other winding. Now note that I've got H1 and H3. They need to be tied to the same line. Why? Because they've got the same instantaneous polarity. All the odds have the same instantaneous polarity. All my evens have the same instantaneous polarity. So I'm going to go and take this one now. I go down that shared conductor. I see that this thing goes through and up. And we see that we have got that other coil that's also going to be connected fully across 2400. We would call this our parallel connection or our low connection. Over here, I've now got a 4800 volt bus. And each of my windings is not good for anything more than 2400. Remember, the lower value is always what the individual windings are good for. Over here, we did not over-voltage the windings. They each went to their proper value of voltage. Now that we're at double voltage, what we need to do is we need to series them together, right? The sum of all voltage drops is equal to my source voltage, and these two are going to be exactly identical. Therefore, they're going to drop identical values of voltage through their counter EMF. So what I see is that I'm just going to have a series connection that goes through like that, all the way from my line 1 over to my line number 2. This is the way that we're going to do our high voltage. Now we know that our low voltage side also had dual ratings. Our low voltage side was rated for 120 to 40, which means that the smaller value of voltage is going to go and be my individual coil, right? Each individual coil is only good for 120 volts. If I'm going to do a 120 volt connection off of this, what I can do, I'll come off of here, where I'm now going to go in on my X1 and come out on my X2, down there to my line number 2. We see that that coil is across 120 volts, and we can go and see that the other coil is doing the same thing. It's going across and going across to my line 2 as well. Each individual coil gets the full line when we're dealing with 120 volts for my bus that I'm putting out here. If I've got 240, what I'm going to have to do is I'm going to have to go and series these two together. So I'm going to go and have 120 series in with another 120, bringing me out to that full 240 that I'm going to go and have. Do we overload any of our transformers at this point, or any of our transformer coils through doing this? Absolutely not. We could mathematically go through that. It's not going to take very long to go and do so, because we already have calculated these currents. Remember how I said before we do connections, let's just make sure we get all these current values so that we know that we're good to go. Tell me, if I were to go and series connect these two together, I could then feed in a total of no more than 20.83 through here, and I could feed out no more than 20.83 through here, right? So I would not be overdoing it with that winding. That winding would be completely fine for me to go and develop that amount of kVA. In fact, if I were to do that, take this, series these together, I would see that I'd have 4800 at 20.8 amps. If you take 4800 multiplied by 20.8, you're going to come up to a value of 100 kVA. It's just going to go and work out. Alternatively, if I did the parallel connection that we had just looked at, each of these would be getting a full 2400, and each of these would be getting a full 20.8, which would mean that I would have 20.8 amps from this one that would join in right over here with another 20.8 that would join in with this one over here, and we would have a grand total of 41.67 amps that we would have coming back out of this thing. If you go and do that math, once again, take this total amount of current, 41.6, the addition of these two together, multiply it by the value of voltage, 2400 because they're in parallel, you'd come out to that 100 kVA again. Same deal on the lower side of the transformer. We're going to do those inside of transformer calculations, but it's one of the ways to make sure that your calculations are correct. And then my PDF just disappeared on me. 1 second. All right, we're back to where we just were, but I just lost all the ink off of it. But that's right. You have it all written down in your books, right? Correct. Okay, let's talk about observing proper polarity. When we go and deal with our transformers, we know that we have instantaneous polarity. In other words, my H1s and my H3s, or all of my odds, will have the same polarity at the same time. So I can do either good things with them, or I can go and do bad things with them. Okay, I'm just going to identify two of these are goods. This is a good, this is a good. This is going to be a bad, this is going to be a bad as well. Let's go and try to copy the goods and stay away from doing the bads over here. What's the big difference between them? Well, if I take a look at this, this is my series 1. I see that I'm going in from 1 to 2 to 3 to 4. If I wanted, I could go and freeze time. Okay, we're just going to go and freeze my line 1, line 2. We're going to freeze it with line 1 positive, line 2 negative. If I were to go and do that, and I were to go and place a positive in, that would mean that this would have to be positive, which would mean that this would have to be negative, which would mean that the other end of the H4 would have to be its positive, and the other end of the H1 would have to be its negative. And if I were to look at that, I would see I'm going from positive to negative to positive to negative. Right? It's like seriesing together two cells, two voltages that I'm going to have. We're going to get the larger value of voltage that we're going to have across them. It's correct. If I were to do the same thing on this one, freeze time, once again, line 1, line 2, we'll freeze time with a positive here and a negative over here. We're going to go and drop this positive in here on my H1. We're going to drop a positive in on the H3. Do they have the same instantaneous polarity? Correct. That's good. They want to have the same instantaneous polarity. H2 and H4 would both be my negatives at that point. This would be a correct parallel connection. Incorrectly done, I'm going to go and cancel out a lot of my fluxes that I'm going to go and have. What's happening on these ones is that my fluxes are aiding each other. That's what they're showing with these little arrows over here, is that those fluxes are working together. In other words, the flux that's created through here is going to go and join to the flux that is created through here and then circle back through my transformer core. If I don't place my fluxes in the same direction, I'm going to be able to go and cancel them out, right? And as soon as I cancel them out, I'm going to go and drop the amount of counter EMF. The only thing that's preventing these wires from acting like a short circuit is the fact that we have got counter EMF that is operating against them. And that comes off of this formula, EG is equal to BLV, like that. My total generated value voltage is equal to my flux density, Tesla's, length, and velocity. If we would nuke this, the flux density, we would get no counter EMF. Over here, we have flux. This one and this one, the fluxes are aiding together. This one and this one, the fluxes are aiding together. Over here, if I freeze time, once again, I have L1 and L2. I've got a positive over here. I'm going to go and have a positive that's going to be generated here. This one over here would also have a net positive that would be trying to be generated on it, but I see that it's going to be attached to my negative side. If I were to look at this, I'm going to have positive to a negative going H1 to H2. And then my H2 and H4 have to have the same polarity, so now it's going to have a negative to a positive. It's the same as if I took two batteries and I went and I series them together back to back, like that. They're going to cancel out each other's value of voltage. In other words, we're going to cancel out the flux inside here. With no flux, we generate no counter EMF, and this thing is going to go and give us basically the equivalent of us bolting a line across from there to there. It's going to be a dead short. It's going to be dramatic, violent, arcs, explosions, people yelling, people getting fired, probably you if you're the one that connected it. It's just something you want to go and stay away from. This one over here is also going to go and have problems with it. It's not quite as severe as this one in a lot of cases, but still bad. Once again, we'll freeze time when we've got a positive here and a negative over there. When we go and place that positive here to my H1, I'm going to go and have my H1 creates a positive, runs through to here where it's going to be a negative. This one over here is going to go and create a positive where it's going to go and run through to a negative over here. But I see that that one is connected over to this positive over here. What we're going to get inside of here is not going to be as dramatic to my lines as it is going to be to these ones here. We're going to get circulating currents inside of these ones, but we're going to go and split them up instead of them being a total series amount that I'm going to go and have. With the cancellation of flux inside of here, there is no counter EMF. Once again, it's going to be short circuit, but in this case, instead of it being just all the current flowing through this in a series path, the way that it did up there, what we have now is we've got two separate paths that the current's going to follow. So I'm going to have one path that is going to be going through here. I'm going to have another path that is going to be going through like that. We'll split the fault current, but it's still going to be a short circuit current that I'm going to have, and it's still going to go and destroy the transformers. Just don't do it, okay? It's not that hard to go and make sure that your connections are going to be done correctly. All that you need to do is make sure that your 1s and 3s are connected to the same instantaneous polarity. My 1s and 3s connected to the same instantaneous polarity, my 2s and 4s connected to the other. Once again, the positive negative does not mean that we're working in a DC system. Transformers wouldn't work in DC. Rather, it's just that we froze our AC. Okay. Write the good, write the bad on your drawings over there. Put a check mark next to them, put an X next to them, whichever it's going to go and be. But you need to know which are going to be good or bad. Now, this over here is where we're feeding power in, by the way, on my high side. So all of these are what would happen, if I were to be feeding power in on my high side. If I do on my primary side, which is my high side at this point, feed in properly, we're going to be fine. We're going to create a massive amount of flux inside of the transformer that's then going to cut across the other side that we're going to be able to generate from. Either one of these is going to generate the exact same amount of flux, which is fantastic, because if I have got this one here where I've got that same value of current, we'll go with that 20.83 amps. 20.83 amps. I see I'm going to get 20.83 amps through all of these turns. I don't know, let's call it 4 turns. Plus I'm going to get another 20.83, or I'm going to get the same 20.83 that's going to go through another 4 turns over here, which means that the total amount of flux, phi, is equal to my ampere turns, right? So if I've got 20.83 amps times 8 turns, that's going to go and give me a certain value. I'm not sure what it is. It's going to end up around like 170-ish or something like that. But we end up with a proper full amount of flux. Will this one be developing the same amount of flux? Well, absolutely, because I'm now going to go and have these in parallel. Once again, each of them is going to get their full proper 20.83 amps. And this one as well, 20.83. Both of these are going to get their full proper 20.83 amps that they're going to go and carry through them through their full amount of turns, right? So I'm going to have, 20.83 times 4 for this one, plus another 20.83 times 4 for this one, and you will end up at the same total net amount of flux. It does not matter how we connect our high side, as long as it's one of these two proper ones. As long as we connect it properly in either series or parallel, we will get full flux. And if we get full flux, that means that we are going to be able to go and drive that flux across to our secondary side to generate voltages off of that one. We need that full flux. Okay, let's go and take a look at our second one that we are going to go and have. Our second side of the transformer over here is going to go and be where we are looking at these things with a proper high side. They're going to do this high side the same for every single one of these, where they're going to go and use it as a 4800 volt bus. They could be doing some of these as 48s, some of these as 24s. It wouldn't matter as long as they get that full flux that's moving across the other side. They're going to talk about a couple of connections that are going to be good, this connection and this connection. They're going to talk about a couple of connections that are going to be bad, this connection and this connection over here. Some of them that are just going to be useless, and one of them that is going to go and be dangerous that we are going to have out of it. Okay. What do we know about transformer polarity? We know that ultimately whatever I have on H1 is going to be the same as what I'm going to go and have on X1. Now, what type of transformer do I have over here? I got a subtractive transformer, right? We see that the H1 and the X1 are directly above each other here. So I've got the subtractive transformer over here. What they're doing with these positive and negatives is they are not connecting these things onto a DC bus. They're just freezing the AC sine wave. They could have frozen the opposite way. They could have reversed all the positive negatives. It would have worked out just as well. But they've given us this positive over here on this line, so therefore this H1 would have to be positive, which would mean that this X1 would have to be positive, and that this X3 would have to be positive. Can I have a positive without a negative? Absolutely not. I mean, if you don't have anything to compare it to, how can you have that? Can you have light without darkness? You know, you need to have one versus the other. So if I've got a positive here, the other side needs to be a negative. If I've got a positive here, the other side needs to be a negative off of there. So what I can do then is I can take these voltages. What are these voltages? These are generated voltages over here. Remember on the high side, they were counter EMFs that we were pushing back so that this thing wouldn't act as a short circuit. Now they're going to be generated voltages through EG is equal to BLV because we got this full flux passed through from my primary side. So I've got 120 volts and I've got another 120 volts. What we're going to do is we're going to series these two together. We're treating it as if it were a battery system over here. And they show that in the next picture over here, that this is basically what we are doing. We took that winding, we've got the positive to the negative, then we trace through, and we connect to the next positive to negative, and we connect onto a line. So we see we've got a positive and a negative. That's what we have over here. Positive and a negative on the output. It is not a battery, it is a transformer, and it will reverse in, the 8.33 milliseconds it reverses, but we can freeze time and we can examine it as a DC circuit just for the point of understanding what's going on inside of it. This is going to be my series low voltage connection over here. My series low voltage connection is going to go and put out my full series value of 120 plus 120, so 240 volts. That we see 120 plus 120, so 240 volts across that bus over there. This one over here, once again, same deal on my primary input side. It's getting proper connection. There's full flux. But now what we're doing is we are going to go and parallel our connections. Once again, H1 is instantaneously positive, so X1 is positive and X3 as well. And then we have our corresponding negatives and negatives. And what we're seeing is we're connecting this positive and this positive together and feeding that out onto a line. These are sources. And then we're connecting this negative and this negative together and feeding them out onto a line as well. They are this same connection over here. Two positives that are tied together and then fed out onto a line to make that bus positive. Two negatives that are tied together and fed out onto a line to go and make that a negative. You'll note that for both of these characteristics that they have over here, whether we're going to be looking at the series or at the parallel, that we will be able to develop full VA out of this, right? If you take a look, we know that the ratings for this one, we did that earlier, were 416.7 amps for each one of these individual windings. Over here, I see it's a series connection, so I've got 460 amps that goes through the whole thing. You can take that down here if you want it. It might be easier to go and look at it here and say 416.7 amps. And if I take that 416.7 amps multiplied by the voltage, which is going to be the sum of these two, 240, 240 times 416.7 is going to get you out to a value of 100 kVA. This one over here, my parallel, each of these is good for 416.7. So that's 416.7. It's going to feed into that node. This one here is going to be 416.7. It's going to feed into that node, which would mean that coming out of here, I'm going to have 833.3 amps that I'm going to go and feed out of this one. What's my voltage across here? Well, it's 120 volts, right? We had these connected in parallel, so it's 120 volts and 833. It's going to equal 100 kVA. 20 times 833 equals 100 kVA. And on this side over here, 240 times 416 equals 100 kVA. It won't be perfect 100 kVA. There's been a little bit of rounding that we've had in some of these current values as we've brought them across, but kVA in is equal to kVA out. We saw that we had full proper connections up here. We had full flux pass through. Therefore, we are going to go and develop full kVA on our secondary sides. Let's take a look at this one over here. This one over here is just a dumb connection. There's really no other way to go and point. It's not dangerous. It just does nothing for us because what we're doing is we've got our proper connection here on the high side, which is fluxing through the core and loading up, this side here, generating these values of voltage. So I get an instantaneous plus here, positive on my H1 and my X1, and I get a positive on my X2, or sorry, X3. That's my X3 connection over there. Over here. So then we got positive, negative, positive, negative. What I'm seeing over here is that I've got my negative connected through to my other negative on that one. Examine it. I'll remove all of my janky marking over there. You see that we got a negative to a negative. In other words, we're going to cancel out our values of voltage. It doesn't create a short circuit. It just takes out the voltage. We have this situation over here where these two are going to have voltage vectors that would be in opposition to each other and therefore would completely cancel each other out. We end up with 0 volts over here. We don't have a positive or a negative. We'd have no instantaneous polarity. It's just a useless connection. Thankfully, it's not very dangerous. This one over here is a bad connection to go and make, because this one is going to go and generate a massive amount of fault current, which is then going to, we're going to see a reflection of that fault current in our primary side as well. How is it creating the fault current? Well, once again, we have got instantaneous polarity. So we see that we've got the positive on our X1. We see that we've also got a positive on our X3. You'll note that for every single one of these, the positive, negative, positive, negative, positive, negative is all created by the high side, by the instantaneous polarity. So now I've got this positive going to a negative, which I then connect over to another positive to a negative. So I've created a series connection, but then for some odd reason, I come back to this line over here. When I do that, I have now created a very low impedance path for current to go and flow. Will there be current? Absolutely. This source is going to start pumping out amps. Those amps are going to go through here. Those amps are then going to go and travel through here and travel back up and through here. They have no desire to go through whatever this load is, that's going to be attached to my bus, right? Current takes the path of least resistance. The path of least resistance is just to run around like an idiot inside of this transformer over here. So we're going to end up with a massive amount of current that's going to flow inside of here. And we know that if our secondary current rises, our primary current is going to rise as well. So on our high side over here, we are going to go and have an increase, a massive amount of current as well. It's not just going to short this winding, it shorts this winding as well, because the currents are lockstepped. They're going to stay together. This one gets to an uncontrollable amount. This one is also going to get to an uncontrollable amount that we're going to be pulling from this 4800 volt bus that we are going to have. It's a highly dangerous connection, this one. This is what it's actually doing over here. If I were to go and take it, draw it out of the batteries, you can see that I'm going to have current that is going to travel through and through. And it's got absolutely zero interest in going anywhere to the bus. There is no net voltage. If I take a look, I got 120 in one direction, 120 in the other. I'm going to have a net of 0 volts across here, but I'm not even going to get around to measuring that because my transformer is going to be on fire at that point already. So yeah, just watch those connections. You will have to do connections as part of your exam. It's just going to be part of what's going to happen. You're going to have some connection sheets. Some of them are going to look like these. Some of them are going to look like true-to-life types of transformers. All right, let's move on to our next step that we are going to go and have. We're going to take a look at the 4 possible connections that we can do using this transformer. We know that we have got 2400 slash 4800, and that we've got 120 slash 240, right? Low high, which tells me that this is a single phase connection. So I can pick any combination. I could go 2400 to 120. I could go 2400 to 240. I could go 4800 to 120. I could go 4800 to 240. That's what they have inside of these ones over here. And what this does is this creates something that is going to be called a voltage ratio. You'll see that underneath each of these, they've got ratios that they've got written. Now, the ratios that they have over here are going to be voltage ratios. Okay, I want you to go and take that and write that onto your binder. That's the voltage ratio for that connection. You'll note that the voltage ratio can go and change. What is my transformer ratio? Well, my transformer ratio is simply going to be the ratio of an individual high to an individual low that I would have for that actual specific transformer, which for either one of these ones, if you were to go and take a look at them, 2400s as being my low value on the high side and 120 as being my low value on the low side, it works out to become a ratio of 20 to 1. Okay, and if you take a look, you'll note that there's twice that my transformer ratio, 20 to 1, matches my voltage ratio on my system. TX ratio, transformer ratio, is 20 to 1. All right, so the 4 connections that we can go and make out of this one would be a series connection. We're going to go through them in depth in a second. I can go to a series parallel. I can go to a parallel series, or I can go to a parallel type of connection that I'm going to go and have off of each of these. Series, we need to make sure that anytime we are doing that, we have got the correct ones connected, right? So we got H1, so it goes through H1 to H2, and then ties to my H3 and comes out on my H4. We got a correct series connection, therefore it's going to be tied to our high voltage bus. Anytime we see the series, we see the higher value of voltage that's going to be associated with it. So this being a series is going to be associated with 4800. This one being a series is going to be associated with the 4800. This one being a parallel is going to be associated with the parallel connection, where I'm going through each of these individually. Like that. Each of those individual windings, and therefore it's going to be the lower value of voltage. Parallel, over here, like that. Same on my bottom side of the transformer over here. I see that I have got a series connection, and therefore the higher of those two voltages, right? It's 122.40, so we're at 240. This one over here is going to be a series, so it's going to be a 240 that I'm going to go and have. And then last of all, we see that we have got the parallel and the low voltage, the parallel and the low voltage off of these. What we can do is we can take a look at the bus to bus voltage. The voltage ratio is simply going to be bus to bus. A bus simply means, a set of conductors that we're using to go and carry power. We use this term all the time, bus bars, the buses, things like that. We're not talking about like autobuses or anything like that. We're talking about an actual strip of copper usually, or aluminum that's going to be used to carry currents along. All I'm doing to go and develop my transformer my voltage ratios is taking my high voltage over top of my lower voltage. So 4800 divided by 240. This one here is 4800 divided by 120. It's 40 to 1. This one here is 2400 divided by 240. Gets me to 10 to 1. This one here is 2400 divided by 120. Gets me to a 20 to 1. Any one of these transformers is going to go and have proper connection of each coil. I don't care which one you would pick or which coil you'd want to go and take a look at. You'd see that each coil has got proper full voltage. And because each coil has got the proper full voltage, it's going to go and have the proper full current, which means that if it's got the full voltage and the full current, it's going to go and have the full VA. All of these individual transformers here dump out 100 kVA onto this low voltage bus. It doesn't matter how that connection is made, but we're getting full flux on the primary, therefore we're getting full generation on the secondary, full amount of current that we have capable of coming out of it. Okay, let's introduce now the concept of a neutral. And a neutral is going to go and give us, a bunch of different connections that we are going to be able to utilize to go and, create 120, 240 types of loads. We're going to pause this video. We're going to create a second video for that.